As I mentioned in video number 2, customer requirements are the most important reason for designing and developing a gas turbine engine. This essentially means conducting a constraint analysis, which initiates the development of a gas turbine jet engine. The design process of a jet engine begins by considering the forces acting on the aircraft, namely lift, drag, thrust, and weight. Therefore, many of the key performance requirements mentioned in the request for proposal are translated into performance relationships between the minimum thrust-to-weight ratio, known as thrust loading at sea-level takeoff and wing loading during takeoff. Understanding these two primary parameters is the subject of this video. Reasonable assumptions about the aircraft lift drag polo and the reduction in engine thrust with increasing fuel altitude and Mach number are the key to developing these relationships. These assumptions do not need to be perfectly accurate, but greater precision reduces the need for repeated calculations. Thrust loading. Thrust loading refers to the ratio of engine thrust to aircraft weight. This parameter indicates the engine thrust relative to aircraft's weight. The value of this parameter significantly impacts the initial design of the engine and forms the basis for creating an engine tailored to specific missions. High thrust loading enables faster acceleration and better performance in aerial combat, making it essential for fighter jets or supersonic aircraft. Low thrust loading is typically seen in passenger or transport aircraft that do not require high speeds, resulting in reduced fuel consumption and operational costs. Wing loading. Wing loading refers to the ratio of aircraft weight to wing area, and is one of the most important parameters in aircraft design because it affects performance under various conditions. Similar to thrust loading, high or low value of this parameter have significant implications. High wing loading, due to the reduced wing area, requires higher speeds to generate sufficient lift, often leading to increased fuel consumption and making takeoff and landing more challenging. This is suitable for fighter jets or supersonic aircraft. Low wing loading allows an aircraft to fly at lower speeds and use shorter runways for takeoff and landing. This makes this ideal for military transport planes or aircraft requiring good performance at low speeds. Aircraft engine system requirements can be estimated when thrust loading is at least equal to the maximum value found in the selected wing loading range. To achieve this, a graph is considered where thrust loading is plotted as a function of wing loading. When driving this graph, several key operational phases of an aircraft must be taken into account. Takeoff from a runway of a specified length, flight at a given altitude and speed, turbine at a specified altitude, speed and rate, and finally landing on a runway of a specified length without reverse thrust. Any combination of thrust loading and wing loadings that falls within the solution space automatically satisfy all considered constraints. At this stage, there are many acceptable solutions, but identifying which one is optimal and why is crucial. Additional performance constraints such as ceiling altitude or acceleration time may also be included in the same graph. By incorporating all known constraints and limitations, the range of acceptable loading parameters will be properly narrowed down. Examples of thrust loading versus wing loading are shown in rated figures, where the left figure pertains to passenger planes and the right figure pertains to fighter jets. The chosen design point is highly sensitive to application and design preferences. For instance, low wing loading seen in C-20A and C-21A airplanes is likely due to short runway length requirements for takeoff. In contrast, high thrust loading combined with low-wing loading in F-22 and MiG-31 fighter jets, largely reflects specific performance requirements for both subsonic and supersonic conditions. Ultimately, constraints analysis is a powerful tool that helps designers navigate error, complex design space, and find the optimal solution for their specific needs. If you enjoyed this video, please like and subscribe for more engineering insights. Let me know in the comments what other jet engine design topics you'd like to see covered. Thanks for watching.